Okay. Good morning, and just now we will open our next session. This is just middle point of our conference, and the first speaker of our morning session is Aleksandr Belov, and his talk devoted to numerical integration of Cauchy problem with singular points. Thank you.
Good morning, dear colleagues. The report is dedicated to numerical integration of Cauchy problems with singularities. Singularities occurring in the exact solutions are a considerable problem for numerical integration. Actually, the position of the singularity is not known a priori. You have noticed that as in a solution of the Cauchy equation, as we approach the pole of the solution, the numerical solution differs from the exact one, so it was considered that numerical techniques are not suitable for such problems, and computer algebra methods were commonly used. Marchuk, at his seminar at the Institute of Computational Mathematics, Russian Academy of Sciences, stated the problem of purely numerical detection and investigation of singularities in the solutions of ODE. In references, there was quite a number of different techniques proposed. They are focused on linear parabolic equation with nonlinear right hand. These techniques allowed to improve accuracy of the different scheme near the singularity, but they did not allow to investigate the properties of the singularity. The first versatile technique of numerical investigation was proposed in 2005 by Alshina, Kalitkin, and Koryakin. It was based on analysis of convergence rate in computation of on thickening meshes. When the solution encounters a singularity, the convergence rate deteriorates drastically. That was the main idea. This technique allowed to solve quite a number of problems in quite uniform manner, and for example, this will break down in plasma and semiconductors, some regimes of nonlinear combustion, and so on. But this method was not robust enough, and it was workable only with help of qualified user. In the present work, we propose new techniques of numerical investigation for singularities in the solution of ODE. They are more robust and simple than the ones known before. Also, we consider problem of solution of a Cauchy problem with not a single pole, but a sequence of poles of integer order. And we propose a procedure of through calculation of several poles. Before discussing the proposed techniques, let us consider some useful methods concerning numerical integration of the ordinary differential equations. The first approach is selection of new argument, the arc length of the integral curve. This method was proposed by Riggs in 1972, and it was systematically used by Shalashilin and Kuznetsov. They published a book in 1999. The main idea is as follows. Let us introduce a new unknown function which equals time, t, and write out the element of the arc length of the integral curve as shown on the slide. Then just perform change of variables. The system becomes autonomous and its order increases by 1. So if we initially had a scalar ODE, now we have system of 2 ODEs in t and u. The main advantages of such approach are as follows. Firstly, the right-hand side has unity length. The vector of the right-hand side has unity length, and it simplifies the integration. A simple example is shown on the slide. This is solution in the time argument, and this is it's how it looks in the arc length argument. Secondly, the singularity corresponds to infinite arc length. So if we calculate up to some finite arc length, the singularity does not fall into our integration segment. This improves robustness of the calculation. Now let's consider which schemes should be used for integration of such problems. A lot of quite versatile schemes are presented in fundamental book by Heirer and Wanner. We considered this book and came to conclusion that some best schemes, very good schemes, are not included into this monograph. Now let us list some schemes that provided good results in our calculations. Transition to the arc length argument allows to employ even explicit Runge-Kutta schemes. They are well known, and I show the formula on the slide. Another good scheme, a class of schemes, is the Rosenbrock scheme. It is semi-implicit, so it's linearization of purely implicit scheme. So at each step, one should solve a linear system of algebraic equations. Among one-stage schemes, the best one is the complex scheme with coefficient 1 plus e divided by 2. This scheme has a second order of accuracy and very good stability properties. Also, it preserves some qualitative properties of the solution, for example, monotonicity. In 1992, Sharkov and late in 2009, Alshin and Alshina proposed two-stage complex Rosenbrock schemes. They had their fourth order of accuracy. The most robust schemes known up to date are the so-called backward optimal Runge-Kutta schemes proposed by Kalitkin and Pashevaila in 2012. By their properties, the schemes are equivalent to fully implicit Runge-Kutta schemes, but due to special recursive form of notation, the complexity, computational complexity, is equivalent to diagonal implicit schemes. The simplest scheme of this class is the well-known backward Euler scheme. The scheme of the second order of accuracy is presented on the slide. Schemes of the third and fourth orders are a bit more cumbersome, but the main idea is very similar. Next, let us discuss the organization of the computation. The program should not only provide the solution, but also the accuracy estimation. Calculation on a single mesh does not provide such estimations. So in the present work, we use the multi-mesh approach proposed by Richardson and developed by Kalitkin and his co-workers since 1960s. The main idea is as follows. Let us perform calculations on a set of meshes. For example, the first has n steps of length h. The second mesh has 2n steps of length h divided by 2, and so on. We perform calculations. We retrieve the solutions on these meshes. Know that the nodes of more coarse mesh correspond with even nodes of finer mesh. And in these corresponding nodes, we can compare the solutions. Using solutions on two meshes and a priori order of accuracy, we can calculate the error estimate, which is presented on the slide. Such estimates, such thickenings of meshes can be performed repeatedly, and by the order of decreasing of the error, we can verify the actual order of accuracy. The basis, the foundation for such approach are the four theorems presented in book by Rябинki and Filipov. The book was published in 1956. Here I present not rigorous but intuitive formulation of the theorems. The first theorem, consistency and stability provide convergence. The second theorem, for linear problems, the consistency order equals the convergence order. The third theorem, for linear problems with smooth enough solutions, we can use the Richardson method described on the previous slide. And finally, the fourth theorem. Consider some initial exact problem. Consider some finite difference scheme that is consistent with the problem and it is stable. Let us perform calculation on thickened meshes and obtain a sequence of finite difference solutions, and assume these solutions tend to some limiting function. The theorem states that the initial exact problem has exact solution, and this exact solution coincides with this mentioned limiting function. Apparently, this set of theorems is the only approach that allows to construct methods which provide simultaneously a posteriori and asymptotically precise error estimates. Now, let us finally turn to the proposed methods of detection of singularities. The first problem is detection of the nearest singularity in solution of ODE. The Marchuk problem is stated as follows. We need to detect the nearest singularity, to determine its type, and to calculate the parameters of the singularity with a posteriori accuracy estimates. Now, the proposed approach. Firstly, let us select the arc length argument as integration argument. Let us perform calculations via some scheme and obtain the solutions T and U in the nodes. Suppose the moment T0 is the algebraic singularity point. Then, in the vicinity of T0, the solution can be presented as Puiseux series. We consider the first term in the series, differentiate it, and obtain a simple relation between the right-hand side f, the solution U, and the singularity parameters Q and T0. We write this, the latter relation in two adjacent nodes, number n and number n plus 1. And using these notations, we derive simple formula for Q and T0. In the course of calculation, we calculate Q and T0 in each node along the integration and analyze its behavior. If Q and T0 tend to some constants, then the dominating term in the Puiseux series is the first one, which we considered, and we can definitely detect the algebraic singularity point. Simultaneously, we obtain some approximate values for Q and T0. In order to estimate the error, we should perform calculations on thickened meshes and employ the Richardson estimations. Similar formula were derived for another types of singularities. For example, logarithm of T0 minus T to the power of Q, and a mixed type singularity, which is a combination of algebraic and logarithmic singularities. Now consider a simple example. At the top of the slide, you can see a test problem which has exact solution with an algebraic singularity. We perform calculations in the arc-length argument via the complex Rosenberg scheme, one-stage complex Rosenberg scheme. On the left picture, you can see the numerical solutions on a set of thickened meshes. Actually, the Rosenberg scheme allows to calculate solution on each step, so the approximate solution has no vertical asymptoty. But at some moment of time, the solution starts to increase rapidly. And as we thicken the meshes, the solution tends to exact asymptote, which is shown with vertical line. On the right picture, you can see computed profiles of T0 and Q on thickened meshes. On each mesh, T0 and Q tend to some constants, and as we thicken the meshes, these constants tend to the exact values of Q and T0. This slide shows accuracies obtained in this calculation. The plot is given in double logarithmic scale. The horizontal axis is logarithm of the number of steps. The vertical axis is logarithm of accuracy. Here, empty markers are the actual accuracy, which means we take exact solution and subtract the numerical solution. And field markers are the Richardson estimations. Here, two calculations are presented for complex Rosenberg scheme and for explicit Runge-Kutta scheme. Let's now discuss them. You can see that the curves tend to straight lines with slope -2, which correspond to the theoretical order of accuracy for the complex Rosenberg scheme. And the Richardson estimates tend to the exact values of the error obtained by comparison with the exact solution. Also, if we perform mesh thickening further, we can obtain errors up to the round of error background. So we can calculate the accuracy of the, we can calculate the T0 and Q with accuracy up to computer round of errors. For comparison, here calculation with the explicit Runge-Kutta scheme is presented, and the transition to the R+ argument allows to employ even the simplest finite difference scheme for such problem. The proposed approach can be used for partial differential equations also. As an example, we considered a classical problem of the S mode of nonlinear combustion. It's a semi-linear parabolic problem with nonlinear right hand. It has a non-exact solution in terms of elementary functions. At each spatial point, there is an algebraic singularity, and the moment of the singularity is the same for all x, and it is determined by the initial conditions. Using the method of lines, we reduce the partial differential equation into a large system of ordered differential equations. Namely, we write finite difference approximation of the special operator and preserve the differentiation in time. To obtain reasonable accuracy, we have to take very large number of special nodes, and the order of this ODE system is also very large, several hundred components. On this slide, you can see the accuracies obtained in this calculation. The calculation was performed by the complex Rosenberg scheme. The left plot shows accuracies for fixed mesh in the spatial for x, and the thickening was performed for the air-cleanse mesh. You can see that accuracies with respect to exact solution decrease with the appropriate second order of accuracy, and at some fine enough mesh, they stop decreasing. While the Richardson estimates decrease up to the round of error, which is shown for their solution U. This behavior of curves is explained by the fact that by using the method of lines, we introduce some error via the spatial discretization. And to decrease this error, we have to thicken meshes in the x variable. Such thickening, the error in such thickening is presented on the right picture. Here are errors of the singularity parameters T0 and Q for thickening of meshes in X. You can see that the error decreases according to the second order of accuracy, which corresponds to the way we introduced the special finite difference scheme. If we perform further mesh thickening, we can obtain errors up to the round of background. Let us turn to the problem of sequence of poles. There are such problems, especially in the theory of special functions, and the main focus is calculate the solution before the pole, in the immediate vicinity of the pole, and to continue the solution through the pole. For simplicity, we consider the problem on example of autonomous scalar ODE. Commonly in known program libraries, direct computation with the Runge-Kutta schemes are used, but as I have already mentioned, near the singularity, the error increases very, very strongly. For Penlever transcendence and for Riccati equations, there are some special methods, but to the best of our knowledge, general procedures are not proposed. The main idea is as follows. Let T0 be the nearest pole of the solution, and it has order Q. Consider the so-called reciprocal function. Its definition is given on the slide. And here you can see ordinary differential equation to which the reciprocal function is a solution. Actually, if the initial solution has a pole of order Q, then the reciprocal function has a simple zero. And to calculate such a zero, there is no problem for numerical integration. We propose the following strategy. Suppose Q is known. Such a situation is the simplest. We perform calculation of U until it starts to increase rapidly. And simultaneously, we check the condition that f divided by u to the power of 1 plus 1 divided by q tends to some constant. Here you can see the practical criteria which can be checked in the program. Consider the node when the criteria are fulfilled and denoted by n star. After this node, we solve the problem for the reciprocal function with corresponding initial condition determined by the last value of u. The reciprocal function decreases by absolute value, passes through 0, and starts to increase by absolute value. 0 of the reciprocal function corresponds to the pole of the initial function u. Simultaneously, we recover the values of u from the values of reciprocal function v. Then, when the reciprocal function becomes too large, we turn back to the initial function u. In similar manner, one can pass through the second and further poles. If q is not known, as it commonly occurs, we can use the diagnostics method described on previous slides to determine the value of q and round it to the nearest integer and limits of the calculated a posteriori error. Here are some generalizations for this approach. Firstly, by interpolation, we can determine the point of the 0 with the reciprocal function and retrieve the position of the singularity. Secondly, this approach can be directly used for systems of ODEs. In this case, one should construct reciprocal function individually for each component of the vector u and use adjacent parameters also individually. Finally, non-autonomous problems. They are sufficiently more difficult in scope of our approach. We have encountered examples when the reciprocal function started to oscillate near 0. It spoiled the calculation considerably. In this case, autonomization procedures are advised. For example, it's reasonable to use the Erkland's argument. Next, in problems with singularities, conventional determination of error via norm of difference of two solutions is unconstructive. The reason is that the computational position of the pole differs from the exact one, so formal difference of the solutions in the vicinity of the pole is very large. We propose to use metrics of the Hausdorff type. The Hausdorff metric for manifolds A and B is given on the slide. It's conventional definition. It is similar to the C norm due to usage of the supremum procedure. Instead of supremum, we propose to use integration, and then this generalization is similar to the L2 norm. Now some example. We have constructed a special test problem with solution which has the third order poles, and the solution doesn't have manifold zeros. The problem is that calculation of manifold 0 is a considerable difficulty, and it is beyond the scope of the present work. So special tests were required. On the left picture, you can see the exact solution. It's given by solid curve. We performed two sets of calculations. In the first one, the order q equals 0, or equal 3 was given a priori, and we checked the robustness of transition from the initial function to the reciprocal one. The errors obtained in this calculation is given on the right picture by black field markers. Here, circles correspond to the solution in the mentioned Hausdorff metric, and triangles correspond to the accuracy of the last calculated pole. We selected the time interval in order to include 5 poles of the solution, and this is the accuracy of the 5th pole, this position. You can see that the accuracy increases in full correspondence with the theoretical order of accuracy. We use the explicit strong equity scheme, and the order of accuracy was the 4th one. And in the second set of calculations, we detected the singularity in the course of calculation using the diagnostics procedures. These errors are shown by empty markers, and the accuracy, of course, is worse than in the first set of calculations, but the difference between the curves vanishes as we thicken the meshes. So we can see that the proposed approaches allow to calculate such problems with accuracy up to a round of error. Now, in conclusion, we show that the classical problem of determination of singularities allows for pure numerical solution. The procedure of detection of the nearest singularity is realized as a software package, and it works in automatic regime. You just press the button and receive the answer with the a posteriori order of accuracy. And here are some works in which the procedures are described in more detail. Thank you for your attention.
Other questions? Aleksandr?
In celestial mechanics, there is a standard
Sorry, I needed the microphone because
okay.
some
But
technical
I can
problems.
speak loudly. In celestial mechanics, there is standard technique of regularization, because the right-hand sides of equations of motion possess a lot of singularities. Do you know this technique?
We do not test them, actually. Also, I think it should be noted that in such mechanics, the singularity in actual motion never occurs, because its probability is very, very low that two bodies just face each other and collide.
It's not a physical theory, it's a mathematical theory, so it's... Yes. Okay.
But actually, I comment the question and this answer. What about the situation with singularities in celestial mechanics? Some of partial cases of three-body problem actually we can not yes, because the quantity of the singularity is infinity. And there is some special way to exclude all the singularity, but by the yes, like Levi-Civita singularity. Okay.
Levi-Civita, it's pair, or
yeah,
not triple.
We did not compare our approaches with this one. Thank you very much.